Hello, it's Keith here, and this is lesson 64 of the platform-specific series of my 650 assembly programming tutorials, and we're looking at the Super Nintendo today. We're looking at my Mintile program. Mintile is a minimal tilemap routine for all of the systems. Now, of course, the Super Nintendo has a hardware tilemap, and so really on this system all we'll be doing is transferring the tile numbers from the software side into the hardware. Now, as I say, being as the Super Nintendo has a hardware tilemap, you might think that that's not particularly worthwhile. You know, why bother using Mintile at all? Entirely fair comment. The real purpose of Mintile was that you can write a program and port it to a lot of different systems with very, very different hardware capabilities. So a system like the BBC has no hardware tilemap. The Super Nintendo does have one, and via this Mintile thing you can actually write the program once and use the Mintile to transfer it through. Anyway, I thought today's example would be a nice refresh of the tilemap capabilities of the Super Nintendo if you're not interested in Mintile itself, and so that is what we'll be looking at today. Let's just fire it up and let's check it out. So as I say, Mintile is a tilemap routine, so we have this scrolling tilemap in the background here. You can see it scrolls horizontally there, and we have these characters on the screen which are simulating sprites. I refer to them in the code as sprites, but they're actually done with tiles at the moment on this version. You can see they can move around the screen and they can go off the screen, so there's the cropping functions in there, and because they're built up with the tile code, we can have less code to port when we're porting this code to a new system. So that's what we're looking at today. Now, Mintile can do horizontal flipping, it can't do vertical flipping. That is something that's going to come in a more advanced version, which is going to come later, called Maxtile. Mintile is my sort of early version. Maxtile is my complete version, if you will, which fixes some problems, adds more functionality. Now, Mintile was designed for a fighting game. I wrote a little fake Street Fighter game called Chibi Fighter on the Z80 systems, and this was written for that purpose. That's why it needed X flip, but it didn't need Y flip. So as I say, that is a limitation of this version. Now, how does the Super Nintendo tilemap work? Well, it's simply a block of memory in VRAM. There's 2 bytes per tile that define the tile number and the useful things like X flip and Y flip. X flip we will definitely need for this, and that's just in VRAM, and we can write to the VRAM. But the problem is we can only write to the VRAM during VBlank. Now, the easiest solution for us is to simply create a memory buffer. So I'm defining a block of memory here. This SNES screen buffer here is at memory address 200 in hexadecimal, and it's a total of 800 in hexadecimal bytes there, 32 times 32 times 2. So that is our buffer of memory that we need to, and we can just write to that buffer, and during VBlank we're going to transfer that buffer into the actual VRAM. So from our code's point of view, we just write to normal memory, and the actual work of getting that into VRAM is being done by our interrupt handler. Now, on the Super Nintendo, our interrupt handlers are defined at the memory address FFCO and onwards. We've got our cartridge start here, but then we've got our 65816 mode vectors here, which is for when the process is in 65816 mode, which is not for my example, it's a 6502 mode example. And here's the ones for 6502 mode, and you can see I've defined custom NMI handler as a label here, and if we look for that, we will see the code that actually does the job of transferring our buffer into VRAM. Now, the way that it does this is that it uses what's known as a DMA, and this directly transfers from the memory to the VRAM, and so this is doing it all for us. Now, to transfer our screen buffer, what we're doing here is we're specifying the destination address, which is actually memory address 0 in this case, and then what we're doing is we are setting up the way that the ports are going to increment here. We're then specifying the write mode here. This is relating to the way that the memory works. There's sort of 2 bytes at each 16-bit address, if you will, so we're just specifying how we're going to write those. In some cases we might not want to write both bytes. We are specifying our destination here, and then this is the destination register here, and then we're specifying this source here, which is actually a 24-bit address because the Super Nintendo has 24-bit memory. We're only specifying a 16-bit address here, and the top byte is 0 there. We're then specifying the number of bytes to transfer, which is 32 tiles times 32 tiles times 2, so that is that, and then we're starting the transfer here. And then the final thing we're doing, because we've actually altered this setting here, we're just resetting that back to the original ink mode, which is what I would use in other parts of my code where I'm transferring data out when maybe the screen's disabled and things, without worrying about the interrupt handling. So that's how we are transferring our buffer, and that makes our job a lot easier. Okay, so the first thing we're going to do is we're going to define the tiles, the bitmap tiles that make up our character and our background. So we've got the code here. It's actually the same as it was before. So we're loading the start address of our bitmap data in memory, the length of our bitmap data in bytes here, and the VRAM destination. This is VRAM 1000 in hexadecimal. That's where the patterns are held. As I say, the tile buffer is at 0 in VRAM. And so we're running this define tiles routine. And all this define tiles routine does, if I can find it, all it does is it loads in 2 bytes and it writes them to ports 2119 and 2118. So there's effectively 2 bytes at each memory address that is addressable in the Super Nintendo memory. So that's why we set the INC on 2118. So we write our first byte to 2119 and then the second one to 2118, and then the VRAM destination will increment by 1 byte there. And so we're just repeating until we've transferred all our bytes there. So that's how we are transferring our pattern data to show to the screen. Now, the Mintile code uses a tile map for the background, of course, and it's a 1 byte per tile map, so these are the tile numbers. And it also uses tile maps for the smaller objects, the so-called sprites here. So this is a miniature tile map for that Chibi-Ko character. So basically this is the tile numbers that make up the Chibi-Ko character, but the source bitmap data isn't the same, or in this case, the system of this case is the tile offset. So tile 2 here and tile 2 here are not the same tile. So even though we're using an 8-bit definition for these tile maps, we can use more than that, more tiles than that for our final code, because we are specifying a different pattern offset when we run the do sprite draw tile map routines. So that's why those numbers are different. Now, when it comes to drawing to the screen, we're simply using the screen base specified here. Now, SNES screen buffer is the RAM address of the start of our screen buffer, and we're effectively skipping the first couple of lines here to centralize our virtual screen. You can see there's a small black area at the top there. So we're adding effectively 128 there to the VRAM offset here, and that is our screen base that's being used when we're drawing the entire tile map. However, when we want to draw one of the so-called simulated sprites to the screen, we actually need to calculate the VRAM destination. Now, the way Mintile works is it draws the tile map as a series of strips horizontally. So we start from a top left corner, either the top left corner of the screen or the top left corner of our sprite, and we draw along, move down, draw along, move down, and we repeat until we've built our object. So if we're drawing a simulated sprite, we need to calculate the VRAM destination. Now, B and C are the X and Y coordinates, and these are in logical units, which is pairs of pixels. So 4 logical units is 1 tile, because each tile is 8 by 8 pixels. So we're taking our X coordinate here, and we're effectively halving it, and we are also rounding it to a number of tiles, and we're storing that in B. The reason we're halving it is because we want a calculation of 2 bytes per tile, because there's 2 bytes per tile definition in VRAM. Okay, so now what we're going to do is we're going to process C here. We're converting it to a number of tiles. We're skipping the top 2 lines, effectively moving down 2 full lines there, and then we're multiplying that up for the number of bytes per line, the 64 bytes per line, so that's why we're doing that. And then we're adding that to our X position, and we're adding the base of our screen buffer here, so we're just the top byte of that screen buffer at memory address 200. So that's how we're calculating our VRAM destination. Now, once we've got our VRAM destination, whether we're using the sort of predefined one or whatever, the Mintile multi-platform code will actually calculate the lines of the tile map, do the cropping for us. All of that is common to all the 6502 systems. So you can see the Mintile series if you want to see about that. There's already a video series on that. It's also on the website. So all you're going to see today is the platform specific code that actually does the graphical job of drawing a single strip to the screen, because everything else is being abstracted into the multi-platform code. Okay, so here is the do strip routine. We're loading X with 0, and X stays 0 throughout this routine. We're then loading a tile number from the 16-bit 0-page entry BCS. Now, BCS doesn't really mean anything. The BCS actually matches the register names on the Z80. This is ported from the Z80, but it's just a 16-bit address, and it points to our tile map. So we're loading in the tile number from our tile map. Now, a 0 has a special function. For the tile map background, a 0 means there's been no change. It's actually a cache of changes for the background, but for the sprites, it's actually an empty part. You see around the character, the Chibi-Ko character's feet here, there are actually no tiles being drawn, and that's what a 0 does within the sprite objects. So we're loading in our tile number, and if it's 0, we're just skipping down a bit. If it's not 0, we've got some drawing to do. But next what we're doing is we're checking tile clear. Now, if tile clear is set to 0, then we don't want to clear this tile. That would be if we're drawing the sprites, because the sprites we need to draw again. But for the background, if we've drawn it and nothing's overlapped it, we don't want to draw it again. You see, Mintile is designed for a lot of systems with very limited memory. They can't afford a double buffer, so it's designed to work with just a single memory buffer, a single VRAM buffer. So it's drawing the changes to the screen only, and that's what we're doing here. We're clearing the entry in the tile map to 0, because we don't want to write it again, because if that tile's not been overwritten, it'll be the same next time, waste of time drawing it. So we would skip over in that case. Now what we're doing next is we're loading our tile number, our single byte tile number here, and we're adding the DE pair here to the destination tile number. So DES is effectively a tile pattern offset, and this is how we can use different tile graphics, tile patterns for tile 1 of the Chibico character and tile 1 of the background, because we can set this DES pair here to a different value when we do our draw background and our draw sprite routines. So that gives some flexibility and means that the single byte tile numbers is not such a restriction now. So that's what we're doing here. Now we are basically writing the first tile into VRAM here. VRAM is pointed to by HL, that is calculated before do strip is executed. And then the first byte is just the tile number, all the bits of the tile number. The second byte is a little bit more advanced. So 2 of the bits are an extended tile number, 3 of the bits are a pattern. The L bit is the layering, whether the background goes in front of the sprites or behind them, so that can be configured at the tile level. And then we have horizontal and vertical flip, very nice, but we're not using any of those here, so we're just adding the carry from the previous stage here. Now, once we've done one tile, we then proceed across the screen and do the next tile. So we're incrementing the VRAM destination here, just across basically 2 bytes. We're then incrementing our BCS source here, that's the tile map. And then we're decrementing the IYL 0 page entry, which is the count of the tiles on the line. Again, IYL doesn't have some clever meaning, it's not an abbreviation. It's just a matching 0 page entry for that function that the Z80 register had on the Z80 system. So that's what we're doing there. And we're just repeating until we've done the entire line. So that's how we draw our unflipped sprites, but our characters can turn around like that, they can turn around. And so what we do for that is we've got an alternate function called do strip reverse, and the Mintail multi-platform code decides when this needs to be executed, and what it does is it walks from right to left backwards through the source tile map. So what we're doing here again is we're loading in our source tile number here. We're basically going to write that to the screen, but we're walking from left to right in VRAM again, but we're walking from right to left in the source tile map this time, so we're going backwards through the BCS tile map here. So we're going from right to left, but drawing it from left to right. So the code is basically identical because, as I say, the Super Nintendo tile map has that XFlip functionality, which some don't have. And so what we're doing here is we are loading our tile in, and we are writing the first byte of the tile number here, and then we're writing the second byte. But you can see this time we've set this bit here, and that is the horizontal flip. That's the horizontal flip there. So that is effectively X-flipping the pattern data. Very nice. And that's all we need to do to get the character to flip around. So that's what we've got today. So let's say this is a simple example. It might be useful if you're looking to refresh how to use the tile map. It's a little bit tricky with regards to using a cache, because we can't write to VRAM except during VBlank, but not too hard. If you liked what you've seen today, please like and subscribe, because I'll be doing another video on tile maps, a far more advanced one, with my Max Tile series, which will be coming up later. That does a lot more things. It does horizontal flip, V-flip. It does double height tiles and things to save memory, and it also I'll hopefully get you working with hardware sprites. Mintile was really just a basic example that was minimally functional to write a viable game, but Max Tile is kind of my my ultimate solution, which hopefully can do any kind of game with it, any game that is sufficiently advanced to be impressive, but is still sufficiently simple to be reasonably portable to a large number of 8-bit systems. That's my hope anyway. So please stick around if you want to see that. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.